Yeah, let me just briefly introduce myself also. My name is Jean-Paul Posma. I'm from the Netherlands, so you can find me online at this address. And all my work that I'm going to talk about today you can also find on this site if you want to know a bit more about it. If you want to contact me, you can contact me at this address. And yeah, I was invited here to talk mainly about jsdares, which is an online programming course that I built a couple of years ago. So I'll just also write this down so that you can also find it online. The JS part stands for JavaScript, and the dares part stands for something like, I dare you to do this, and the course consists of a number of dares or sort of exercises or puzzles. So yeah, by all means, try it out yourself online at some point. I don't work actively on jsdares currently. Yeah, like you said, I work for some other companies. But I'll mainly talk about jsdares now. But afterwards, I'm open for any questions or discussions. I've never done such an hour-long seminar before, so I have no idea what will happen. I've prepared some stuff to talk to you about here. But I've written it all out, so I can email it to whoever wants it or something like that. But the benefit of you and me actually being here means that we can actually have some kind of two-way interaction. So I would much rather have you just interrupt me whenever you have a question or a thought or some way that might relate to your experience with teaching or programming. And I would love to explore some kind of different tangent based on what you guys come up with. And actually, active participation is a very important way of learning, which I'll talk a lot about, actually. So, just to get started with some background first, my story starts in late 2011, and I was studying computer science at the University of Oxford at the time. And I was looking for some kind of final project. And at the time, I was reading about, the history of computing, and one article really struck me, and that was the classic As We May Think from Vannevar Bush. I don't know if any of you knows it, but this was in 1945, and he foresaw that we would have the complete knowledge of the world, at our fingertips, at our immediate disposal, which we have now, as the internet, of course. But he imagined, what the world would be like once you have that. He imagined that, in the past we have amplified, all the different senses and actors that we have. We have amplified the hand with different tools like hammers, and the eye with the microscope. And he would imagine that this new thing called the computer would amplify our minds in some way. And in many respects, this has sort of come true. In many fields, we use the computer to do things that were previously, impossible. But in one field, I'm afraid, we don't see it as much, which is education. Many people still learn using physical textbooks, not using this promise of computing at all. And if we do, we hardly amplify our minds. For example, we read an article on Wikipedia, which is basically just plain text and some images. And we have plain text for thousands of years now. Or we sign up for one of those MOOCs where we watch videos of professors, but we have moving pictures for over a century now. And we have these online forums and things like that, but that's more of a replacement for transportation. People don't have to be in the same place. But as you all know, distance learning is pretty big now. But it's hardly a way to use computing to amplify our minds. People can do it from everywhere, but that's something else. And actually, today Google came out with a pretty cool educational tool. And in their announcement, they actually said, you don't learn piano by watching videos from virtuosos. And I think that captures it pretty well. So yeah, a computer is not a broadcast medium, but a tool to make us think better. And that's sort of the background that I'm coming from. I wanted to use this idea in some kind of way, like how can we really use a computer in a different way in education. So for my dissertation in computer science, I wanted to make something that would teach some kind of subject and leveraging as much of this computing power that we have as possible. And my advisor told me, well, you're studying computer science, so teach programming. So my goal became to create an interactive programming course for children that should be a truly amazing interactive experience. So the first thing I did is I interviewed a couple of teachers of programming at my old university and at a youth center where I volunteered, and they told me, just start off with something simple, some kind of imperative language, but have them make something meaningful, like a game or a website, something real. So I decided to use JavaScript because it's ubiquitous on the web. Everything you make with it, you can just share with your friends, and it runs in a browser, so that's great. Hence the JS part. And they also told me that trial and error is very important. With programming, you can often use some kind of interactive console where you can type in some commands and you will see immediately what happens, and that's pretty great. And I always compare this to playing an instrument, right? So if you hit a key, you immediately hear what you're doing, and if you're playing and you hit the wrong key, you immediately can correct yourself. One thing we should be careful about, though, is just by playing music by trial and error doesn't teach you about music theory. So that's a catch, but still. So also I felt that the interactive console is not really enough. You can try out some new commands in it, but you don't have direct feedback when you're actually writing a program. And I'll show you right now. Because usually when you're programming, you have to write something and then you hit compile, and then it will generate some kind of executable, and then you hit the run button and it runs the executable, and then you see what you actually have written, what the program actually does. And then you have to go back and fix some things and edit some things and then compile again and then run again, and it takes a long time. So the first thing I did is I just made a zero response time compiler, which just instantly compiles and runs the program when editing it. So pretty basic. If I just write something like a hello world here, you will immediately see, it's a console log, I think, yeah. You will immediately see here at the bottom the console, the hello world statement popping up, and I can do some more advanced things, of course. I can just make a basic loop and go through the statement a couple of times. I hope you can all see this. If you can't see, please let me know. So you get some immediate feedback. It's only on the bottom there, so you need a pretty big screen, and the resolution is not very high now. So in the next prototype, I actually show you the program and the output side by side, so that works a little bit better. So yeah, that's the very basic, I suppose. And another thing that I added here is a step button. Now, just a basic debugging tool where you can go through the program step by step. Here you have some kind of assignment. I is 0, and then it checks whether I is still smaller than 10, which it is. So it goes here and it calls console log 0, and then it increments I, checks again, etc. We all know this. And while you're doing this, you see here underneath in console the numbers popping up while you're going through. So this is a pretty basic debugging feature. Only this is a bit more complicated than most debuggers, because it actually shows all the different assignments and such, even in loops, as exactly what's happening. I can also do something like this. I can have like a more complicated expression in here, something like I times 2 plus 10, and if we go through this, we will actually see all the different steps of the computation. And I think this kind of thing is pretty important, because one of the things you have to learn when learning programming is to learn how the computer thinks, right? What does the computer do exactly? So if you go through it like this, you see every atomic action that the computer is taking, and you can really try to understand it. Now in practice, I haven't seen many students actually using this button, because why would you click a button and things happen on the screen that you don't understand and don't care about? But actually I found that when teaching, a button like this is actually pretty useful to sort of go through everything and show exactly what happens.
Just a question. Is this dependent also on proper code structuring so that the things appear on the left? So do the students also have to worry about how the layout of the code?
A little bit, but I actually enforce that with the compiler. This language that you see here isn't actually real JavaScript. I've created a sub-language called JS that's smaller than JavaScript, but is a proper subset. But I enforce some kind of code structure. For example, something very silly that I just didn't get around to fixing is that if you put this one on a new line, this is just a different coding style. But actually, in my language, this is the only correct one. And this one doesn't work. You actually get this error here. Perhaps there is a bracket missing. So this is also something that I wanted to do, like these error messages over here. Usually when you're programming, you get some kind of obscure message, syntax error, or maybe, if you're very lucky, some kind of help. I expected this or this or this. I expected an expression here or a symbol like that. On line 3, and then you have to go to your editor and find where line 3 is, and it's somewhere on that line. But here, if you make a mistake, if you forget a semicolon, for example, you get an error message exactly where the semicolon was supposed to be, saying you need a semicolon there. And actually, this is very easy to do with compilers. I mean, you get a lot of contextual information while you're parsing or running through your lecture, things like that. So why wouldn't we have like contextual error messages like this? Right, let's see where we are. So let me go to the next prototype. Because while I was making this first prototype, a guy named Bret gave a presentation called Inventing on Principle. I don't know if any of you have seen it. It was really great. If you haven't seen it, you should really check out this presentation and all the related work also. It has inspired a lot of features that I put into this editor. Actually already in this prototype, when you step through it, like these things here on the side where you see this information of what happens to the variables, even though you've already stepped further. That's something I basically stole from his presentation. So in the next prototype I decided, so basically what his main message was in his presentation was that creators should always have an immediate connection with the thing that they're creating. So a painter, they should, when they draw on the canvas, they should immediately see what happens, and they do. And when a musician plays a piece, they immediately hear what they're doing. They don't have to first play everything and then hit the play button to play it back to them, which is what we usually do with programming. So this actually fitted really well with what I was working on at the moment. And he showed some prototypes about things that might help when you're programming, not necessarily learning programming, but actually R programming in general. So I implemented some of those features just to see, can we do this in the real world, because it looked really, really nice in a prototype, but can we actually do this for real, and does it actually help? So here I have this interface, and I'll just copy over a program. Let me see, this is a nice one for the console. So this program, it just prints a multiplication table, right? So you get all the different multiplications between numbers in there. And one of the things that were suggested was you should really be able to play with numbers and change some variables really easily to sort of get a feeling for what's happening. So instead of just changing this loop counter to something else by hand, like this, you can see, you know, what happens on the left there. I can just hold the Alt button, it's this button, and all the numbers and colors and things like that, they light up. And I can just see what happens if I drag this one to make it smaller. You see this number really sort of represents how many lines are printed. So you get a feeling for what this number does. And this number also represents how many lines are printed, but something different happens, right? It's the first line that's being printed becomes a different one. And I can play with other numbers that are in here. For example, let me play with this one. This does something very different. This sort of plays with the colors that I just put in there for fun. Because it changes how fast the U changes for each line of code that is being printed. So that's pretty neat. You can just play around and sort of get a feeling for what's going on. And another one is this one. This is the highlight button. So if I hold my control button on the keyboard here, I can go over a line of code and see what it does. So here this one prints the first line there, and this one prints an empty line, and then, you know, this function prints this whole bunch. And if I don't know, put some more stuff underneath here, and you can see by highlighting that these correspond exactly to those. And the same way goes if you're looking at the output, and if I go over here. So if I want to know where this particular line is being drawn, I just highlight it like this, and you will see it show up on the other side, the actual statement that draws it. And the same here. So you get this really close connection between the code and the output. And that's also really what programming is about. Is, you know, your program has some kind of output, but you sort of have to do this mapping in your head that, you know, this statement should output this, and you can try to verify it by adding some debugging statements around it. But here you get this really immediate connection. Another thing that I did for this second prototype is the ability not just to step through everything, but also to be able to go back. Because it's actually pretty silly when you think about it. Why can't you just go back in a traditional debugger? I mean, you have to you can just execute the entire program and remember everything that happened during this execution. And then you have this whole log of the execution trace, which you can just explore at will. And this is actually a very rudimentary way of visualizing and this execution trace. I mean, this is still very linear. You're at one point in time, and you can go to the next statement of the previous one. So for the next prototype, I've implemented this quite differently. I'll show you in a minute. But why shouldn't you be able to just, you know, go back and forth? Did I actually understood what was happening here? What happens if I just change a variable here? Well, it actually updates, and now it runs with some different variable. So you should be able to always interact with the program and explore it. I can show you a little bit of how I actually implemented this, because this whole program just compiles to. It is just JavaScript, so you can just run this in the browser's console if you would like to. But I actually compile this to some different JavaScript. So this is the JavaScript that's actually being run by the browser once it has been compiled. The student will actually never see this. I just put this in for debugging purposes. But basically what I do is every statement and every expression in the program I wrap with my own function, so that I can do some additional checking. For example, if you subtract two strings from each other, it wouldn't give an error message in regular JavaScript, but it does in this JavaScript. So I can do runtime error checking, but I can also log everything that's happening at an expression level. And I basically get full control over the complete execution. So it means complete sandboxing. If I make this an infinite loop, just by putting true here, you will get at some point somewhere an error message that the program takes too long to run, too many statements have been executed, so we'll just abort it. because otherwise, you know, you can easily make the whole browser pretty irresponsive if you just let infinite loops run like this. But you get complete control over it, which is very useful. So for the next prototype, there are actually 2 prototypes in between, but they are quite buggy because I haven't maintained them. So I'll just skip to the real thing that's online right now. I don't have internet access, but this runs on jsdares.com. And I'll first show you what I would have shown in the other prototypes. So this playing around with the console is kind of nice. You can explore the different features that you might want in an editing interface for education. But they're not very interesting to many students, right? I mean, printing some algorithm on some console is not very engaging. So I figured, you know, what did those teachers tell me that I went to? They said, you know, you should be able to create something meaningful, like a website or a game. And actually creating a game, I think, is probably, you know, the most interesting thing you can do with programming for many children. You don't want to be able to just create any game, but you know, you want to be able to create a game like the actual professional game designers would do. So I took the HTML5 canvas, which is a modern web component. It's actually used by many professional game designers, for example, who create mobile games. So I thought that would be a pretty nice pretty nice way for children to learn games. So I'll just copy over an example here to show you how this canvas works. Yeah, so you have these commands like filling some kind of rectangle or starting some kind of path, and you can draw all kinds of different shapes with it. And it's completely standard. This is the standard interface. If you any program that you're creating with this, you can also copy paste to some other website and it would run on its own perfectly. But yeah, the problem that I got myself into is that I wanted to have all the features that you saw before, where you could highlight things and change things and all that. I wanted to have that for this canvas as well. So actually it works pretty well. In this version, this is already a couple prototypes further. I don't have any buttons for highlighting things, so you can just move the mouse over things and it will automatically highlight the statement on the right, and vice versa. I can just select any statement and it will show exactly what it does. If I just copy and paste this one, I can show you the difference. For example, I can change this a little bit, just play with it, and you see, you know, this one is being drawn here and this one is being drawn there. So yeah, I also removed the button for being able to play with numbers. You just have to. You always get this interface for free. You don't have to press any buttons. And I saw that actually when doing something like this, you know, it seems that students are actually using it because they see these buttons these numbers light up, and what can I do with this? And you click it, and you can sort of see this icon that you can drag it around. And it seems to work. Even though you can't really tell whether or not they're using this highlighting, because it's very hard to see if they're using it explicitly. It seems to me that it might actually work. So for the implementation details, it's quite tricky actually to get this to work. This way, so from a statement to the output is relatively simple. You just save everything that you're drawing on the canvas, and you repeat that when you're highlighting one. But the other way around is a bit trickier. So if I hover over a square here, how do I know that this statement here has to be highlighted? Well, I don't really, because this canvas, this HTML5 canvas, only stores pixels. It doesn't store shapes. It doesn't tell you you're hovering this particular shape right now. It only tells you you're hovering over a pixel with this blue color. or black color in this case. So that's no use. So what I do is I made a mirror canvas. I can show you in an older prototype where I still have the debugging features enabled. Just copy paste this over here. So if I show you the mirror canvas, you will see this. And so basically for every statement that's being drawn, I draw the exact same thing, only on a different canvas with a different color, and I generate some random colors that map back to the statements and then keep them in a list. So when you move your mouse over one of the squares, you just look in the mirror canvas and you can find the original statement based on its color. So yeah, this is all pretty neat, and you can learn how to make games with this. We will come to like the interactive games in a minute. I'll just show you something else, which is this stepping through. Originally I had the step buttons, but you know, you're at one point, you can move forward or backward. This bar underneath really allows you to jump to any position in the program and see what's happening exactly there. So I can see, oh, okay, here it's checking for the 9th iteration, and it's doing some calculation there, and then we go a bit further, and then it draws this shape here. And for this program it's not very interesting, of course, but if you have a bug, you can really go through and try to find where exactly the program went wrong, and try to see how that happened by going a little bit back, a little bit further, and try to exploit the program like that. And also just fix this in place so it will stay like this, and just play with some variables to see, you know, what would have happened if there was a 5 here. Well, we would have been at some different iteration already. Works pretty seamless. But you know, for learning how to make a game is a pretty big step if you don't know programming at all. If this is the first time you're seeing programming, you know, this is a pretty big step already. So I talked to my advisor, and she suggested, well, maybe you should have a robot driving around in a maze or something like that. This is actually borrowed from Seymour Papert. I'm sure a lot of you have also heard of his seminal work, Mindstorms, which basically talks about these physical robots that children can drive around in the lab using a programming language called Logo, and they have these pens inside, and they draw like huge shapes on these pieces of paper on the ground. And his vision with teaching like this is pretty deep, actually. He imagines like you can go to France to learn French, because you're really immersing yourself into this different culture and language, and this way you sort of take in French and the French culture and all that. In the same way, you would imagine, you know, the computer using such a robot or something would be like a math land, where you would immerse yourself, you know, making these shapes, these geometrical figures, and you would sort of automatically, while simply playing, learn math. And I can show you an example of this. If we go to this robot shape, just remove some stuff here. So if I just have a clean maze like this, like nothing else on the screen, I can just make the robots drive around freely. So you can have it drive and turn, and it will do exactly like you tell it. But it only has a few commands. Like you can drive a little bit, you can turn, but you can also specify how much it should turn. So it should turn, for example, 30 degrees. And you can, of course, wrap this into some kind of loop and have this done, I don't know, 50 times. And you would get a big circle, right? And this is actually something you can ask children to do. You can ask them, you know, how would you let the robot drive a circle? And usually they come up with something like this. You let it drive a little bit, and then it should turn a little bit, and they can come up with a solution like this. And it might seem pretty silly, right? It's very basic, it's just a circle, but actually what they would have learned is the differential equation for a circle, which is exactly this, a little bit further and a little bit turn, and that's how you can draw a circle. Or you could imagine an exercise like this. How much should this should the robot turn if you wanted to just drive and then come back? Well, you can play around and see, you know, what should I do to make it go and then come back? Well, it should be 180 degrees, right? At least with how we've defined degrees. And then you could have an exercise, well, if you wanted to drive and then turn and then drive a bit again and then come back. So another step, how much should it turn at each step? Well, 120 degrees. And with exercises like this, you can sort of, well, teach that the rule is that all the turns combined should be 360 degrees again. So you can really, you can ask them to write down, you know, sum up all the different angles, and they will find, you know, it's 360 and 360 again. This is one of the examples from Papert's Mindstorms, actually. So even though they might not immediately, you know, get a deep geometrical understanding or like all the theorems that we know from geometry, they do sort of get a feeling by just playing around. You know, how do angles work? How does the robot respond if I do this or that? And for that you really need an environment that lets you play around and explore and things like that. But for programming, I mean, this is real great for math. But I wanted to teach JavaScript, so I wanted to create a JavaScript land in which you would be immersed and you would learn JavaScript. And this is really great for that, but I made some puzzles in which you have these walls and you would have these goals that you would need to reach. And I'll just show you a couple and see, you know, how a student would work through them, and at each point learn a bit more about well, how programming works. So let me go back to the actual jsdares.com as it is now. So, I've already completed the first one, but anyway, this is the first one. You have to drive it to the green square, and it actually starts like this. No, I think like this, with some commands in there. You can already see how the robot can move around, and you have to navigate it to the green square. So a student might see these commands as would be the first time they would ever see, you know, real programming statements, right? So they either would have no idea what to do, or they would sort of recognize that there's a turn right here, and that probably does something. Oh, and it's actually highlighting. I don't know if you can see that on the screen. If I highlight, if I go over hand this drive, this might do something. It actually does this, right? It's being highlighted, so that's the idea that I also implemented for the robot. And they can see, oh, here it drives a bit forward, and then left, and then it drives a bit further, and then it turns, and then it drives. So we should probably have it turn it here. So let me just copy paste that, which is fine. And then, lo and behold, it turns. And then perhaps we should have it drive again, and drive maybe a bit further. And if you have a really clever student, they would actually notice this number in here and maybe even see that you can sort of play with it by dragging it, or just type in any number that would work, and it would have written their first program. And they submit it, you get some points, happy. And then you can continue to the next one. So I won't show you every single one. I'll just skip one here. Let's go to here. So here it's basically the same thing. You have some setup commands, and you have to complete the program, and you already know how to do it because you already did it twice. but here an additional constraint is being added. Move the robot to the green square in as few lines as you can. And this sort of sets the stage for the later exercises, because once you have this limit on the length of a program, you can sort of force them to use cleverer things like abstractions or loops and things like that. You don't want them to always program out exactly what it has to do at every point in time. You want them to be able to extract a function. And so that's what we'll come to pretty quickly. So here, for example, this is a pretty interesting one actually, because it shows in this preview, you know, you can do it like this. You have to visit them all, and you have to do it like this. But the text actually says something like, programmers always look for the fastest solution. Can you find a fast route? And many students actually find out that there's a route going here, there, up here, and then here, which is far less commands than doing it like this. And this is actually quite important, because it sort of gives the students a feeling of, you know, beating the teacher, which is pretty cool, and some self-confidence and motivation. So in the next exercise, we actually introduce functions. So I've set up a function here. It's like, this is how it's normally done. I've already tried it a bit at home in preparation, but this is how a student would encounter it the first time. So you would have a function here that drives it a little bit and turns it and then drives it again. So it makes this movement like here or there. And you can just try to repeat it. Even when you don't know exactly what a function is, you can sort of get a feel for it. You know, you see these repeated patterns over here, and then when you copy paste this, like everyone does, you see that, you know, a little squiggle is added, and you do it again and again, and then you run into a problem because you can't do it there anymore, so you will have to do some manual stuff to actually drive it correctly, and then when you're getting back, you can use this function again to make this movement, but then downward. And this is the first time students learn about a function, and usually you don't actually have to tell them anything. They can just copy and paste this a couple of times and struggle with it a little bit, but usually they actually get it. And in some cases, you know, some teacher assistants might be nice or necessary, but in many cases this just works, even though they might not know exactly what a function is. And then in the next case, we pretty much start with a blank slate. You know, there's this statement on the screen that really doesn't do anything useful, so you might as well just remove it. So you're really starting from scratch, and you have to implement a function to do this, because otherwise you will have too many lines of code, and when you submit it, it will tell you, you know, no more than 20 lines, and you had 40 or something, and it won't work at all. So here the students are sort of being forced to think, and they have learned something in the exercise before. They can go back and look at the syntax. You have this function thing, the thing between brackets, and try to copy paste that into here and see what happens. And a lot of students sort of struggle with this initially. That's why I made the pattern that you see here really clear. Like, they shouldn't have to worry about, you know, finding out what the pattern is that we have to abstract here. That should be really clear, so that they can really focus on applying this technique that they just learned a minute ago. And I think I think it's really important that when you're doing such a thing like this in the classroom, that you really let them struggle with something like this. Sometimes when I'm teaching with this, I give some little pointers like, hey, you might want to use a function, like to put this in your function or that in your function or something like that, but very minor things. Because once they have completed this, and once they've completed this on their own, it's a big achievement, right? This is the first thing the first time then that they would do programming and actually have used something that they learned in a meaningful way, and that gives a huge sense of accomplishment and motivation and self-confidence and all that. So that's really important. And then for the next couple of exercises, I introduce things like function arguments, and that usually works pretty well, even though they might not understand exactly what a variable is. And there might even be necessary, depending on what age you're targeting with this, to add some more intermediate exercises in between. But it usually works pretty well. And then at some point, I want to make the shift to drawing on the canvas, because eventually the goal is to learn how to make a game. Yeah.
Sorry, before you go on, because you mentioned age. So the children that you have been teaching this, how old are they?
16 or something usually.
16?
Yeah. Yeah. But I've also tested this with younger children. There it very much varies, how well they get on with it. But I've seen even quite young children, just going through this really quickly. But I think it might be better for younger children to have some more intermediate exercises so that they can really practice what they've learned a couple of times before moving on. On the other hand, you also want to get to this part, which is a lot more fun, the drawing on the canvas. I'm really starting to learn how to make a game now. To do that pretty early. So this is sort of an introduction where you have to. This is how it starts. This is an introduction for learning how to draw on the canvas. So again, it's pretty simple. You can sort of look at the code that's already there and sort of play with it, see what happens. Let me just do something like this. It isn't perfect. It should be there should be a hole cut out there, but let me just submit it so that you can see what happens. Basically match all the pixels that with what it should be, and you get this pretty overview of what you did right and what you did wrong. And in this case, I didn't get it completely. I had 96% and I needed 97%, but I did it in only 3 lines, so that's great. So yeah, you can complete this, and then at some point you go to the next one and you get the same shape that you did before, but you have to abstract it. So here we have the same picture drawn over and over, and you can use what you learned, apply a function, and you even have to do a little bit of math here, like adding some numbers together. But then again, I think this interface where you can see what draws what exactly, this one draws that, and this one there, and this one there, so we should probably have a 4th one, and the numbers are, pretty, they show me already that this should probably be 250, but if I don't see that, I can just, try to play with it until it sort of matches. And that's pretty much as far as I want to go with showing you these exercises. After this, we get some things with the console again. I haven't really figured out, to be honest, how to go from this really basic stuff to actually learning how to make a game. I mean, that's probably a pretty long road. You need to introduce events or some kind of interactive elements at some point, but I didn't really have the time to do that. What I did do is actually make the interface, the editing features that should really help when making a game. So let's just assume that the student somehow got to this point, and this is also sort of this teaser that we have on the front page where you can play this game and you see the code right here that's being executed. So if I know from the previous exercises that I can play with numbers like this, and a lot of students actually start playing with this game once they have figured out the interface, you can sort of play with this and see what this does. And I win this game now, right? But I can also see what all the other numbers do. Oh, this is something like this, and oh, I can add some here. There we go. So it's pretty easy to play with this already. So on the implementation side of this kind of stuff, what would have happened if I would have implemented this in exactly the same way as the other exercises that you saw, then when I were to change something here, the entire program would restart. Because that's how it works, right? You change something, the program restarts, and you immediately see what's happening. That's not what's going on here. Because if I change something, the program just keeps on playing, and you sort of interactively update what's happening with the program. So that's something special that I do for interactive programs. I detect, I know whether a program is interactive or not, and then when someone changes one of the functions that's being called as part of an event handler, then I detect that that's a special treatment. It's a function in an event handler, and I only update the event handlers and I don't restart the program. It's also possible that you really do want to change something that's not in an event handler. For example, here you have some initialization of some variables and things like that. So if I add something here, I don't know, some dummy thing which I want to initialize, then I don't want to suddenly restart the program also, because it would be very confusing if somewhere you could edit the program and it wouldn't restart, and at some other point it would restart. That's very confusing. So what I do here is, you might notice that the restart button sort of starts flashing pretty gently, indicating that if you want to see your changes reflected, you should hit this button and it would be reflected. Of course, it doesn't do anything. I can also hit the pause button, because really, if once you have an interactive program, you have this additional variable, time, and you should be able to sort of see what happens if you go back in time or go further in time, just as you would be able to go through the program execution trace at any point, however you want to. You should be able to do that with time as well. This is also something I took from Bret Victor's presentation. So if you just go back here, you can go back in time and see a couple of events, and at each point in time you will see what kind of event it is. This is a set timeout event, and it will show you, well, this function was being called, and if I just lock it in place here, I can go through the entire execution trace of this particular event. You can just go through and see the entire canvas is being cleared and everything is being redrawn. Maybe that's a little bit inefficient, but that's how this program works right now. I can do this for every event. I can, if I just use the mouse a lot now and pause, I can go back and see what happens at the mass event. And it doesn't really do that much. It only sets a new pedal X, and then it waits for the next event, for the next drawing event to be called, and it uses the new position. So that's all that's happening here. It's not very exciting. So yeah, you should be able to do things like that. But if you really want to be able to try and understand the behavior of the program, of an interactive program, it's pretty important that you can see what a program does over time. So if I'm playing with some variables now, something like the speed of the ball, you will see that at this event it will have changed, but what happened in between, what's happening over time. So what I can do is I can see, okay, where's the ball being drawn? Well, that's here. Then there's this blue bar in front of this function, and if I click this, you will see exactly what happens over time. Also something from Bret Victor's presentation, but he did it only for some kind of fixed event. I figured that the function level is a pretty nice level where you can introduce this interface. So you will see exactly what happens over time. So if I now rewind, then this is what is going to happen with the ball. And now I can play with some variables and see what actually is going to happen if I change things. And what should happen is there is a bug in my program. It's an intentional bug, but you would have never found this bug unless you would have some kind of interface like this that would actually show you the behavior over time. So in some particular cases, it can bounce off to the top and then keep on bouncing between these blocks. Even though it should have just, had moved down. So if I play this, the program executes in a completely deterministic way. So this is exactly what's going to happen. And that determinism, that it executes always in the same way, is actually a pretty important property of these programs if you want to implement something like this. Because the way I implemented it, it's pretty performant. Like while you're playing, it's all pretty smooth, and that's because I don't want to log everything all the time. I just take a snapshot of the entire system, so all the program variables, whatever on the canvas, all that. I take a snapshot of it, and then I store a couple of events that follow. And from this snapshot and these events, you can rebuild whatever happens as long as the program is completely deterministic. So you can just replay it, but with logging turned on, and then you get the entire execution phase like you did before. So I do a snapshot every, I don't know, 30 or 40 events, and from that you can build everything in between. So yeah, I think that's pretty much everything I wanted to demo and explain a bit about the implementation. I have tried this with a couple of classrooms. Every now and then I go to a school and sort of use this for to see how it goes and to teach some programming. And I think especially the exercises with the robots and all that works pretty well. You also see, the children usually have a keen interest in learning this, but there should be some kind of bridge over that gap that's still there. But especially those exercises work quite well. I think that's it. Thanks a lot. I would welcome any more questions. I mean, I've been talking for an hour now alone.
Okay, thank you very much.
Yeah, thank you.
Questions?
Do you teach also other languages, programming languages?
No. I've really tried to focus, and that's also why I implemented even a subset of this language, because I didn't want to bother with all the different features that the different languages have.
Because my question is, sometimes it's important to understand the feeling of programming, not just to learn the single language, but just to get this feeling how the programming is basically working, how to learn it. And would be really useful for kids to have some tools to get this feeling of programming, not just programming some particular language like JavaScript or something.
No, I totally agree with that. I think that also motivates a lot of different approaches. For example, the drag and drop languages, right? Because there you don't really have to type anything. It's a bit more accessible even than this. But I think an approach like this also empowers the students because they are actually learning something real. They can actually use the skills that they learn in the first half hour when going through this course, because they're actually going to do these canvas exercises, and that's an actual API that you can use. And I think that's pretty motivating.
Yeah, but it's very cool. It's very cool. Then you can see, you change something and you immediately can see. It's very cool, and just ask it.
Yeah, but I think of course it's important to have different programming languages. But I'm not quite sure myself yet what the best way would be for really first-time programming. Whether that should be even more accessible, perhaps with some drag and drop language like Scratch, for example, or whether you should start out with something like this.
Thank
I follow on from Michelle's question. What's the youngest age where you use this successfully?
Well, I think this kid was actually, had already done some programming, perhaps. He was, I think he was 9 or 10 or something. But he just rushed through everything and did it all in an hour or something. But I haven't tested it with like a larger group of younger kids.
Yeah.
Yet.
So it's mainly sort of 16-year-old and
something like that. But I've heard of other people also using this in different classrooms, but I haven't fully inquired which ages they did and which settings exactly. Yeah.
I might have missed this in the first half, but what are your plans for the future? You mentioned.
Oh yeah, I
that,
didn't mention that.
Are you planning to develop it further, or what?
I'm not actually. This was mainly a research project. It's all open source out there, and I've also included sort of a level editor so that you can make your own stuff. So I invite everyone to participate in some way, but I'm not developing it further myself right now. There is, however, another company that has taken a lot of ideas and like algorithms that are used for doing this performantly and things like that, and that's called Code Combat. And they are actively working on it, and it's also completely open source. So that's this site. Oh, I don't have any internet, but you can see the URL of Code Combat.
So it is possible to both add new activities and also add to the actual IDE, right?
Yes, it is possible. Some people have done so, but it is also, I mean, it's a pretty steep learning curve, I suppose. The code base is pretty rough still.
Yeah, I was just thinking, one of the things that I find very interesting about this is it's not so much as a teaching tool, this is actually a tool for real programming.
Yes, yeah, and that was
very
the
much
goal.
what Bret Victor's ideas is very much about.
Absolutely.
This actually is the way programmers should be thinking when they're writing code. This is the best approach to take. And the real challenge is how we can incorporate that into our daily thinking and our daily work when we're writing code.
Yeah,
so I think this is really good.
Yeah, so when I was making this, I sort of had two goals, and that made the work that I actually did a bit scattered in a way, perhaps. But my main goal was to make a programming course. But my second goal, inspired by Bret Victor's talk, was to demonstrate that these ideas that he showed in sort of quick prototype way actually work, and that you can make them run fast, so that they would apply to everyday programming. And this might not be like the best problem domain because students' programs tend to be fairly small. So if you get to really big code bases, then this gets a lot more difficult already. But it works, and it works for any program that you can put into here. And yeah, that's what I wanted to show.
And you said earlier the work you're doing with the startups now includes some work where you're creating educational materials. Is that building on this, or are you taking a completely different approach?
It is quite a bit different, but we do have sort of the same philosophy on teaching and on everyone. This idea that the computer should really help you try to understand in such a visual and interactive way, where you can immediately see what are you doing and what's happening. But I mean, there we also have things like simulations for physics, or a piano course is on there now, where you learn music theory, and it's very diverse, much more diverse.
So, but you're not thinking of, or Versal is not thinking of, for example, taking this and putting this as a widget.
Yeah, maybe.
Then
I
make a course around it.
I might actually do that. Yeah, if I find the time. Yeah, because this works perfectly, embedded in some larger teaching context of some kind of course with perhaps some additional videos of instructors. Or what I was also thinking about is, there's already this competition element in here, because you can get a certain number of points and you can see the high score on the home page and sort of try to. What's actually pretty nice, the replayability of the exercises is pretty high. Once you've learned about depth first search, for example, you can write a program that solves every of those robot puzzles in 4 lines. But you have to learn a theory for that first, and at every point you learn some more theory. For example, you get to loops, and you can go back and make your earlier programs a little bit shorter, and you learn about some other things, and you can make it even shorter. So this competition element is pretty nice, and I think that also transfers to other domains, like the gamification is a pretty hot topic, I think, in education in general right now.
Any further questions? Okay, thank you very much again.
Thank you.